You ever see those giant spinning towers on the horizon and just wonder, how do they really work? Well, today we're going to break down the awesome physics that turns something you can't even see, the wind, into the power that, runs our world.
So it really boils down to this one big question, right? How do you turn something totally invisible into enough electricity to power millions of homes? It kind of seems like magic, but nope, it's pure physics.
Okay, so to really get how this works, we've got to start at the beginning. We need to understand the energy we're trying to grab. And it all kicks off with a super basic concept, motion.
And that concept is called kinetic energy. It's a pretty simple idea, really. If something is moving, it has kinetic energy. And wind? Well, wind is just a ton of air moving all at once. That means it is absolutely packed with this invisible energy just waiting to be harnessed.
So the whole trick is figuring out how to convert that energy. And it's basically a three-step process. First, the wind's kinetic energy physically pushes on the rotor blades, making them spin. That's step one. Step two, those spinning blades turn a shaft inside the turbine. So now we have rotational energy. And finally, step three, that shaft spins a generator. And a generator is this amazing device that uses magnets and wires to turn that spinning motion into actual electricity. It's so simple, but honestly, it's brilliant.
But, this isn't just guesswork. Engineers don't just put up a turbine and hope for the best. The amount of power you can actually get is all governed by a very specific and very important mathematical formula.
And here it is, the wind power equation. Now, I know, it might look a little scary with all those symbols, but don't sweat it. We're just going to focus on the two parts that really matter the most, the two things that engineers can actually change and then have the biggest impact.
So those two key players are A for area and V for velocity. Area is basically the giant circle the blades make when they spin. Engineers call it the swept area. And it's pretty obvious, right? Longer blades mean a bigger circle, which means you capture more wind. But the real superstar of this whole equation is V, the velocity, the speed of the wind.
And this is why wind speed is so incredibly important. See that little 3 next to the V? It's V cubed. That means the power you get doesn't just go up a little when the wind blows a little faster. Oh no, it goes up exponentially. This right here is the secret sauce to getting huge amounts of energy.
And check this out. This really drives the point home. If you double the wind speed, you don't just get double the power. You get 8 times the power. 8! That is a massive difference. And it's exactly why the location of a wind farm is everything. Finding a spot that's just a little bit windier can mean a gigantic leap in how much electricity you can generate.
Okay, so if faster wind is better and capturing more wind is better, then you'd think the goal would be to just, stop all of the wind, right? Capture 100% of its energy. Well, here's where it gets really interesting. There's a catch, a universal speed limit, if you will, on wind power.
And it's a totally logical question to ask. If the whole point is to extract energy from the wind, why not just build a solid wall that blocks every bit of wind and grabs all of that energy? Well, it's because of this really cool paradox. Think about it. If you put up a solid wall, the wind has nowhere to go. It just piles up in front and stops. No more flow means no more motion, which means no energy is captured. At the other extreme, if you have no blades at all, the wind just zips right through, and again, you capture zero energy. So the answer, the sweet spot, has to be somewhere in the middle.
And believe it or not, a German physicist named Albert Betz figured this all out way back in 1919. He did the math and calculated the absolute theoretical maximum amount of energy you could ever hope to pull out of the wind.
And here it is, the magic number, 59.3%. This is famously known as the Betz Limit, or Betz's law. And it's not an engineering problem. It's a fundamental law of physics. It means that no matter how smart we get, no matter how amazing our technology becomes, we can never build a wind turbine that's more than 59.3% efficient. It's literally impossible.
And of course, in the real world, we don't even get that close. The actual practical efficiency of a turbine is called its power coefficient. That's the CP from our formula earlier. Because of real-world stuff, like friction on the gears and aerodynamic drag on the blades, even our very best designs today only reach about 35 to 45% efficiency, which is still really impressive, but it's a good bit below that hard physical limit.
So if engineers are stuck with this hard limit on efficiency, how do they keep getting more and more power out of the wind? Well, the answer is pretty straightforward. They just build bigger. And I mean much, much bigger.
Just look at this timeline. It's pretty wild.
In a little over 20 years, the average size of a turbine rotor in the US has more than doubled. We are deep in an era of absolutely giant-scale engineering.
And this really puts that scale into perspective. We're talking about hub heights taller than the Statue of Liberty. The rotor diameter, the circle the blades make, is longer than a football field. It's just mind-boggling. And why so big? Well, it's a 2-for-1. Taller towers get up into faster, more consistent winds, and those massive blades? They increase the area, in our power formula, sweeping through a much bigger chunk of the sky and grabbing more energy.
But this brings up a question you've probably had if you've ever driven past a wind farm. You see a whole field of these things, but some are spinning like crazy and others are just stopped, completely still. If the whole point is to make power, why on earth would they ever stop spinning?
Well, it's all about safety and operating limits. Every turbine has what's called a cut-in speed. That's the wind speed where it starts spinning and making power. Then there's the rated speed, where it's making the most power efficiently. But, and this is the crucial part, it also has a cut-out speed. If the wind starts blowing too hard, say around 55 miles per hour, the turbine is programmed to shut itself down. It's a safety measure to stop it from literally tearing itself apart.
And it's not just high winds. A turbine might be stopped for something as simple as routine maintenance. But here's a reason you might not expect. Sometimes they're turned off because they're making too much power. Yeah, really. If the demand for electricity on the grid is low at that moment, the grid operators will actually ask the wind farm to shut down some turbines to keep the whole system in balance.
So the next time you see one of those giant turbines spinning on the horizon, remember, you're not just looking at some blades on a tower. You're actually seeing this beautiful story play out. It's elegant physics, it's a clever workaround for a universal law, and it's an absolute marvel of modern engineering on a breathtaking scale.
And that kind of leaves us with one big final question. We've pushed the physical size of these things to incredible limits. Now we're moving them offshore to chase even stronger, more consistent winds. So, after mastering the limits of physics and scale, what's the next big hurdle? What's the next great challenge we're going to have to engineer our way around?